Welcome everyone to Riot's Lunch and Learn series, where we highlight our awesome sponsors and the technology that they are building. My name is Rachel Newberry. I am the program director at Riot, supporting innovation with our corporate partners as well as early stage startups. We are very fortunate today to have Delano Seymour, CTO of EDJX, on the line with us, as well as Laura. And Dr. Laura Roman leads marketing for EDJX, and I would love to introduce her first to share a little bit about EDJX, and then introduce us to Delano, who will be talking to us today about serverless computing. So really glad to have you all. Laura, please kick us off.
Rachel, thank you so much. Hi, everyone. It's Laura. I'm CMO of EDJX. Really excited to have you on the call today. We see this in short as a kind of a masterclass, a chance for for developers to brush up on skill sets. Delano Seymour, who is our illustrious CTO at EDJX, is going to walk us through the EDJX platform, and he's going to talk about the great value of mesh compute and storage as a feature of the platform, features of the platform in particular. And the end game here really is to ensure that you're signed up for the platform. The link is in the meetup, and I will be sending you a follow-up email with a link again. And to follow what EDJX is building and what Delano is going to lead you through today, in short, to understand like what this new platform offers, what it offers for the developer, how fast it is to spin up apps. And then we'd love for you to hack away. We just opened up the platform. It's new, and we'd love to get your feedback. So with that, Delano, over to you.
All right, thanks, Laura. Good morning, everyone. My name is Delano Seymour, and I'm the CTO of EDJX. And today we're going to talk about using serverless with mesh compute and storage. We can see that today that we have more and more devices that are generating data. And video constitutes much of that data that is generated. Estimates show that we will have 1 trillion devices by 2030. 1 trillion. While the bandwidth that will be required for those devices will outpace the supply that we have going to the cloud. So one of the things that we can do to mitigate that risk is to bring some of that processing local to the device itself that needs it, or local to the user that needs that processing power. A latency could be as high as 160 milliseconds round trip to go to the cloud and back, while some applications need a lot less latency than that in order to perform well. So this is sort of the goal of EDJX. We create a edge computing platform where you can write apps on the edge. Well, what are some of the use cases for EDJX? If we look in this next slide, we have various different ways in which you can use EDJX, some of the different use cases. For instance, you might have a smart city application, things that manage the different elements like parking and other features in a city. You might also have traffic management, automate autonomous drones and being able to control those drones. There could be transportation related systems that have to have low latency communication, national security, autonomous systems. Well, there's a long laundry list. And CDN, it's still out there. Lots of people use CDN, and we can help to improve that communication as well. But what we'll do next is let's build an IoT application. Let's see how this works. We have here an application where a user who's going to come into a campus would like to have access to different areas of that campus. Okay, so first thing we're going to do is set up an inexpensive camera. And these cameras will be located in various locations around the world. And these cameras, the purpose of these cameras is to focus on the people as they walk in and out of that campus. If that person has access, then we will allow them in. If they don't, we won't. So what we want to build is an application where the user does not have to wait in line. There's no stopping. They could just walk right through. The system will validate who they are, using face detection, and then allow them to pass through that system. We also want this system to be dead simple for the users to use. So having no way to type in anything or having to put information would actually make the system a lot simpler. So let's think about how we would set this up. I mean, we live in a modern world today, and in our modern world, we use the cloud, right? So let's use the cloud for this purpose. And with the cloud, we'll probably have to pick a particular region. So let's pick one of those regions. What we want to do is be able to send data from the camera to the cloud, allow the cloud to process that data, do things like face detection, and then send a message back to open or close a door. Very simple application. So once we choose that one region, we're gonna put that compute in that region so that it can do that processing. But we do have a problem. We have many regions, or sort of many campuses that are spread all over the world. So maybe what we can do is to put the compute in all the regions that are close to all the different campuses that we have all over the world. Now, this could be a good solution, but it does create some maintenance hurdles. We have to maintain the application in 3 different places or 4 different places instead of 1. But we'll just go with this for now. Now, that application needs data. So the first goal will be, let's put the data in the primary location, the central location, the home location. Now, that will be okay for all the users in that location, but the other locations are going to have latency issues trying to read and write to that database that's in a different location. Okay, well, let's use the same process that we did for the compute. We're going to put storage in all of the locations around the world. Now, this will definitely improve our application usage. All of the different users in different locations will have their data in their location, and when they come in and out of that campus, things should work pretty well. Except that even the cloud itself is far away from this location. Imagine sending data from that camera all the way to the cloud, waiting for a response to come back, and then finally open the door a few minutes later. I think that will cause our application to not want to be used by our users. It'll create latency. We'll have long lines. So what are some of the problems we have? How do we solve this issue? Or what we have to deploy hardware and software in each building, maybe, instead of using the cloud at all? What if the employee visits one of the other locations? Will he get the same experience as in his home location? And what about the company-wide view of the system across all campuses? I mean, that's probably going to also suffer, because now I have to get data from each of these locations and bring them to one central location so that I can look at a holistic view of the company. So we find that we have several problems that we have to overcome. One, very complex. We just went from a simple application to a very complex solution. And that complexity will get worse as we add more and more locations to our application. Latency, the speed of light is constant, so we cannot make that faster. So how do we communicate from one end of the country to the other as fast as possible? And then, of course, we've got data. So I got to get the data from one point to another point as quickly as possible as well. All of these represent a problem that we need to solve, a few problems that we need to solve. Is there a better way? Can we solve this in a different way? Well, let's use something that most of us are familiar with, a Wi-Fi router. Everybody probably has a Wi-Fi router in their home or at their place of business. And we probably use our cell phones or our tablets to connect to this Wi-Fi router, which gives us access to the internet. Now, if you're close to the Wi-Fi router, you don't have any problems. Everything works well. But as you move further and further away from that Wi-Fi router, your signal will decrease and eventually it will drop altogether. Well, one solution is that we can add an extender, right? This creates a second network, so that now if you move further from the first network, you could disconnect and reconnect to the second. But then you have that issue of connecting and reconnecting between networks. We sort of look at this as the cloud regions that you see. If you go to one of our clouds, you go to region A, you can put all your data in region A, but what about region B? What if you need to move it to another country, another location? Well, now you got to figure out, how do I get my data and my compute to region B? And that could take a lot of time and energy to set that up. So a good solution in the Wi-Fi world is to have a mesh Wi-Fi network, where you would have nodes in different rooms, or you'll have nodes all throughout your workplace, and you just connect to one network. And all these nodes cooperate, and they give you connectivity as you move from room to room inside of a building. So your phone now stays connected and gets the highest quality of connection no matter where you are. But what if we could take this mesh concept? We already have a mesh network, so we don't want to create that. What if we take that mesh concept and apply it to compute? Now we can have compute that operates similar to that mesh network we described, where all of the different nodes cooperate to create a supercomputer. So now if you need to compute something, you can connect to any one of these nodes, no matter where they're located, all over the world, and you'll get the same quality and experience as if that node was in your local city or home or town. And as you move from one place in the world to another, you maintain that connectivity and you maintain access to that compute. But compute by itself is not enough. So we've also added mesh storage. Again, these nodes work together, they cooperate to create a super drive. If you upload a file in one node, it will be available in another part of the world on another node. You just have to connect to that system. Now, if you take both of these two technologies and put them together, then you have a mesh edge fabric. So now we have a platform where all the nodes cooperate to give you compute and storage, no matter where you move around the world. Now, how do we do these things? Well, one is we use a peer-to-peer network. So each node communicates with all the other nodes in our network, and they cooperate, they exchange information using a gossip protocol about where data is, where compute is, and where the actual user is. And so now we can bring the compute and storage close to the user so that they get the best quality of service as we possibly can give them, no matter where you are in the world. Now, to do some of this, we've also added serverless functions. Now, why serverless? Well, serverless gives us the ability to create code that can execute based on an event. Okay, so one event could be an HTTP request. I make that request, that creates an event, then I execute my function based on that event. That function will start and end in a specific time frame. So now I can route my request. The first request go to node A, that function executes, the next request could go to node B, and that function executes. So now I can be anywhere in the world, and every time I send a request, I could possibly hit a different node depending on where I am. So let's go back to our application we started with in the beginning. We can simplify this IoT application. If we add that mesh fabric into the equation, now my camera could communicate with any node. That node could be in the same country, might even be in the same city, or possibly could be in the same building even. Once it hits that node will process the request. Maybe it does the face detection, then it might hand it off to another function. That next function's job is to look up that particular user and find out if they have access or not. Then I can hand it off to a third function. That third function will be the one that actually opens or closes the door. Now you notice that these arrows point to two different nodes. Each request could be processed on different nodes. They could even be processed in parallel so that you can get the highest quality of your application. And any node can process this request. Therefore, if any one node goes down, gets destroyed, gets removed, the system still operates. So it's a very autonomous system. But I do have more than one location. Guess what? This can happen across the world. So I can have different campuses all communicating on that single fabric, that single mesh fabric all over the world. Same application deployed once, but used in many places. So this new architecture that EDJX is providing gives us a couple of different benefits. Number one, you'll notice at the bottom, we're going to have billions of devices. I mentioned that earlier. And those devices need to communicate, get compute done, store data, retrieve data wherever they are. So we sit in between the actual device and the cloud, or the actual user in the cloud. So we don't remove or replace the cloud. We just help enable or help to make the cloud even better. So things like complexity gets reduced, cost gets reduced. We get an ultra low latency. We can connect everywhere and anywhere. And then we also have another feature where we can add sensor hosting. So you can have sensors attached to these nodes so that you can do things like LiDAR and video and any type of like temperature sensors connected directly to these nodes, and those nodes could be put in that local environment. So I want to give you sort of a demo of this. Like, let's see this in action. So I have logged into our console here, and you can see that we have a little dashboard that shows all the requests that were made. And in this dashboard, we see that we have one application and one bucket in this account. We also have a node in this account, and then we have 27 global nodes that could be that also can be used. And we can see where they're located around the world. And then we can look at our compute, network, and storage. Now, if I click on the application section, I can see this one application called Parrot. Now, what's an application to us? An application to us is a set of functions. Now, if you think about it, most applications are a set of functions. But what makes us different is that these functions in and of itself does some compute based on an event. And then that function can actually communicate with another function. And they can be sort of daisy chained together to create a whole service, whatever you choose. Now, this particular application is a simple one. It only has one function called speak. I can see some of the stats on this function, requests that were created, network traffic that was used, the compute that was consumed, and the trigger. And I can also see that this function was written in Rust, and it's running on our WASM runtime. So everything that was done in Rust was then compiled to a WebAssembly file. And that WebAssembly file is what you deploy to us. So your code stays with you. You could put in GitHub, do whatever you need there. But after you compile it, that WebAssembly artifact is what you would send or deploy to our platform. And now I can also put some limits. So I can say that, hey, I don't want this to use more than 16 megabytes of memory, for instance. So I can choose, okay, what will I set my allocated memory to and restrict it. If it goes beyond that memory, it will be automatically terminated by our system. I can do the same for how long it runs, the duration of that function. I could say 5 seconds, no more. Now keep in mind, that's a long time because our functions operate in the micro/millisecond realm. So they happen really, really fast. I'm going to take this URL that was automatically generated. And since this is triggered by HTTP response, if I was to then save this and paste it into this browser, you can see that now that function was executed. It's a very simple function. It just returns welcome to EDJX. But let's dig into what just happened. So I made a request using a URL. That request was then sent to a DNS server because it needs the IP address, not the URL, in order to do its work. So that DNS server is one that we have created. So we've created our own DNS servers. So when that request hits one of our DNS servers, it will then triangulate where that request is coming from. Then it'll use that information to find a node in that location and we try to find a node that's as close as possible to you. And then it will return the IP address of that node so that you can communicate directly to that node. Once it hits the node, this URL encodes the address, the application that we want to use, and the function we want to run. It will then execute that function and return the results, all within a millisecond of time. So we can look here and see that we have requests that have hit the system. We can see that this request ran for 345 microseconds. So micro, millisecond, month, minute, hour. And it used 364 bytes of network traffic in order to do its work. And it has 0.00054 gigabyte seconds of compute time. And you can see that we can do these requests all at the same time. We can do these requests one at a time, doesn't really matter. We can also take a particular request and look at the logs from that request. So I just spit out some simple logs, but you could put your own logs in there. And I can look at any activity over time. I didn't make any changes today, so there are no activity. I can also look at the logs across all requests if I wanted to. Now let's take a look at the buckets. Now this is where we store data. So you would look at this as similar to like S3 in Amazon or cloud storage in Google. You can upload a file or many files inside one bucket. In this case, I have a logo and I have an HTML file. If I click on the logo, I could grab that URL, and again, I could just paste it into my browser, and I could see it's just an EDJX logo. I can also take this HTML and take that URL, and I could put that in the browser as well, and I have a website, just basic HTML. So I can store data in the bucket, and I can serve data in that bucket as well. And you'll notice that I even can link to that logo that we mentioned earlier, and I can execute that function all from that same simple website. When I upload files like this, I also have some other features. One of those features is I can pin this file to a particular node, right? And of course, I would have to own that node for this to work, but I can pin that file to that node, or I can have that file, that upload notarized, meaning that every node that sees that file gets the exact same data, and they all report that, yep, it's the same data before it says that it's done. So I can also do that as well. And with each of any one of these files, I can look at its version. So we have version control for these files, and I can look at any activity like uploads and downloads. Of course, I have to change the date on when that was uploaded, but we can do that as well. The next thing I want to show you is domains. So if you notice these long names, you probably don't want to give that to your customer. So we also have a domain, a DNS system. So you can create a domain. This one is demo.edjx.network. You can create records like A records and NS records and CNAME records. But also you can do request routing, which is what we've done here. So I've said that whenever I have an exact match where this domain, demo.edjx.network, this URL is sent to me, redirect it to a different URL. We can do certificates as well. And then of course you got activity. So now if I go in, instead of doing that long name, I could just type demo.edjx.network and I get this URL, which then I can execute the function. So now you can see how I could take domains and buckets and applications, and I can create my own application, my own service. It could be a face detection, AI, it could be something that computes files. Whatever you can dream, we can build on this network. There's one other service that I can't show through the console, but it does exist, and that's our key value database. So if you want function A to store some data that function B needs to have access to, then you can use our key value database to store that data in that as a key, as a value with a key, and then another function can retrieve that data straight from the storage. Last but not least, I just want to show you that all of this runs on nodes, and these nodes live in different parts of the world. In this case, I have only one. This node lives in Kansas, and I can look at all the requests that were processed on this node over the last year, for instance. I can look at all the requests. I can look at any logs from that node too, so I can manage that system. So this is sort of the high level view of EDJX and what you could do with EDJX and how you can write code. We do support C++ and Rust today, and we're hoping to add Go and JavaScript even later. But with those programming languages, you should be able to write any software you wish on this platform. Now that's my demonstration of the platform. I just want to switch back and say that, you can get started today. Go to console.edjx.network. It's free today, so you can take it for a test run. Try it out. Let us know what you think. And if anybody has any questions, I'd like to answer those questions now.
Thanks so much, Delano. We've got a few questions in the chat here. First, a couple clarifying ones. So the EDJX platform does not use edge-based model detection with cloud-built models?
So no, we don't actually create the actual applications. We have created a platform to run those applications at the edge, right? So you would have to actually, have your own models. You have to bring your own code, and then we can execute and run that code.
Great, thank you. And are we talking AWS multi-region Lambdas here, or a different architecture entirely?
This is a completely different architecture entirely. With AWS Lambda, everything's in a central location. Now, there could be a region 1 and region 2 and region 3, and you can have different places all around the world, but they're still centralized, right? Regions don't talk to each other. What we've created is a system where all of the nodes in the system talk to each other. That allows you to be anywhere in the world, and the system sort of adapts to where you are. So it moves close to where you are, no matter if you're in India one day and in the US in another day. That system will move your data and your code next to you. That gives you the best performance and low latency.
Thank you. And a follow-up to that, Delano, Travis said you had mentioned using existing cloud services and this running underneath it.
So you can use, so we don't prevent you from using existing cloud services. In fact, we augment those cloud services. So anything that you need that it needs to be close to the user. Things, for instance, things that move like drones, where a drone is moving from point to point. We don't want that drone to have to travel all the way back to the data center. They can hit a node that's close to them instead of making that round trip. But then that particular node that's close to them could do some processing and then send information back to the cloud, right? It could put stuff in a database, put in any type of system that you have. So we don't prevent that. In fact, we use Google Maps, for instance, for that mapping feature that you saw earlier. So everything can still work together, right? What's in the cloud and what's on our platform.
Continuing that thread. So edge devices here refer to edge devices with backhaul and not IoT devices or nodes on their own. Is that correct?
All right, so let's sort of get the terminology right. There's a device like a camera, right? That device will be at some location somewhere in the world. Then you got the cloud. And the cloud is where you probably store your data for like the last 7 years. Might be stored in the cloud, for instance. Okay, we sit in the middle. So we sit between the device and the cloud. So that device needs to get to a node that's in its same building, right? Or needs to get to a node that's in the same country or the same city. That's where we come in. We will be that node. In fact, that device can communicate with that node, and then that node could return a result right back to the device in real time. So that device gets what it needs fast. And then once it needs to send some sort of summary data or it needs to send roll-up information, it could send that back to the cloud at any time.
Thank you. One from earlier, can subdomains be programmatically generated via API? Yes,
so we do have an API. You can use our API. Everything you saw in that console, you can do via an API. In fact, that console is built on our API. So yes, you can create domains. You can create domains, you can create apps, you can create buckets all through the API. It's a REST-based API.
Delano, how does EDJX handle latency in countries without proper cell access where satellite backhaul needs to be used?
Right, that's a great use case for EDJX, because what can happen in that environment is that we can put a node in that country, right? And then all the devices can communicate with that node. They can actually run applications on that node. They can get data and store data on that node. And then that node takes care of distributing that data back to the other nodes in the system. And those nodes could be just down the street. That node could be in another country. That node could be back in your home office. And it can also distribute data back to the cloud too. So now you don't have to have a really fast internet pipe. It could be something like satellite, because the time it takes to upload that data can happen overnight. It doesn't have to happen right away, but the application and the users get access right away, because we can compute and collect data and return data right away.
Thank you. And yeah, all these great questions are from Travis. Travis, I'm gonna maybe I'll ask you to unmute if you have anything to comment verbally. He says that he works with the Helium LoRaWAN network.
Mm-hmm. No, I just wanted to say thank you. This has been a fantastic presentation, and I'm very happy to have been invited over here. It's been a great talk, and it's interesting. I signed up for an account, and I'd like to play around with this. It's something that we do a lot of work with. I guess countries where cellular access isn't really available or isn't very widespread. And so sometimes you have to look at, centralized backhaul. And a lot of times that's using satellites, which, kind of throws latency to the wind. So, yeah.
Yes,
very interesting here. And thank you so much for your time today.
Thank you.
Thanks, Travis. Other questions for Delano? We have a few minutes if others want to add things to the chat. Delano, while we're waiting for anything that might be remaining on folks' minds, what's the best way to engage with EDJX or reach back out to you or Laura? How can folks find more information?
All right, so we do have a sort of general email, hello@edjx.io. You can just send general information there, or if you have specific support information, then you can send something to support@edjx.io. Also, you can go to our console at console.edjx.net, or our website is www.edjx.io. You can get access to all of this on our website. And you can see all our details, see how we use the platform, see how much it costs. We haven't enabled the costing yet, but that's something that will be coming in the future. But for now, it's free. So we would like if you can give it a try, give us your feedback. If you want something improved or something added, that would be awesome. We're looking for that type of feedback.
Yeah, I'd also just say, I think even more specifically, please feel free. You can just drop me a line, Laura@edjx.io, and I will funnel everything to Delano or Vipin, to the correct person, our dev team within EDJX, if that's easier. Absolutely happy to do that. Maybe, Delano, you can talk for a minute about some of the apps, maybe the internal hackathon that we did in spinning up apps on the platform, and the languages that we support right now, and what's coming.
Yeah, so we did an internal hackathon, which was pretty interesting. And we gave everybody 5 days to build an app, 5 days. And we got 5 different apps from 5 different teams inside of our company. One app was what we call Edge URL. We actually, in our documentation at docs.edjx.net, there's a section, a tutorial section, where we describe exactly how we built that whole application. In fact, we even open sourced it. So all the source code is there. You could download that source code and build the app yourself if you want. But it creates a sort of a URL shortener. So take a long URL and shorten it to a small one. We've seen that a lot when you use Twitter, because you only got 256 characters or something like that. And so you want to shorten that URL to have more space. So we created a whole app using our platform to do just that. There was also an app that tracked like someone with dementia. So as that person moved outside the boundaries of a particular geofence, then it will send alerts to their caregiver. And we did that on, going outside the boundary. Another part of that app also tracked their normal process. Like say they always go to the store at 10 o'clock and then they come back. But if they go to the store at 10 o'clock and don't come back, then that's an anomaly. And then the system will again alert their caregiver. So that was another app completely built on EDJX. There was a third app that did a sort of testing system. So it ran tests against their website. So you can test your website from different parts of the world. That was a cool app as well. But we had various different types of app all built within 5 days and fully functional, which was awesome.
Mm-hmm. Yeah, our whole value prop of how that we make it simple and how fast was definitely proven. We drank our own champagne as it would, like any good company would, before we opened up the platform. And again, this is new. We just opened up the platform in the last 2 months. So we're really eager for your feedback en route to pricing. But right now we see this as a chance to build in C++ and Rust. Obviously, as the platform evolves, we'll support more languages, but this is fresh out the gate. I think even maybe the WASM runtime, like the value prop of WebAssembly, maybe it's worth talking about that for a moment too, Delano.
Yeah, sure. So all of our code is compiled down to WebAssembly. WebAssembly gives us some good properties. Number one, you can compile to it. So therefore, we don't need your source code. We just need the compiled version. Number two, when it runs in a secure sort of sandbox where that code cannot really jump outside of that sandbox. They can't communicate with the hardware, read the disk. We do all of that through what we call our Edge library. So we have created a library of APIs where that function can make a call and get a file from, for instance, our KV store, or they can get a file from the object storage, or they can reach out to the internet. All that's done through our API. And again, that's all available on our documentation site, docs.edjx.net, which describes step-by-step how you can create these types of apps. And it has like a link to GitHub where you can see all of the code to access the KV store and so on and so forth. So we use WebAssembly a lot. Also, it can run whatever we deploy compile to WebAssembly can be executed on any platform, right? Including the one we create, we call it Edge OS. And so it can, you could run that WebAssembly even in a browser, even if you wanted to.
Delano, a couple more questions here in the chat. First, is this a closed source project or are there open elements?
Most of it's closed source, but we have an open platform, meaning that you can write any app you wish. We don't prevent you from writing your apps. And, you can do whatever you wish, really. The software that we've built, the main purpose is to manage the hardware so that you don't have to. So that's what we want to take off your plate, right? You don't have to worry about hardware. You don't have to worry about is my hardware in the right location. You don't have to worry about if your hardware is up or down. You don't even have to worry about really deploying to which hardware at what time, right? We take care of all of that for you. Our software takes care of all of that for you. So all you have to focus on is writing your code, deploying it to our platform, and then letting it run.
Great. And Tim McLaughlin asks, what is the process to get more local nodes? Is that something that the app builder would have to create, the end customer, like the campus you mentioned?
Mm-hmm. Okay, so currently we have a program, we have a partner program where we work with different companies to put nodes in different places around the world. But if you wanted to put your own node, you could work with us. We can open that feature up to you, and then you can actually deploy your own node. Right now, we're sort of got it closed into our partners, but in the coming months and years, we want to open it up so that you can create your own nodes at any time.
Can hardware be DIY built?
Can you repeat that? Sorry.
Can hardware be DIY built?
Hardware. Yes, it could be any hardware. As long as that hardware can run free BSD, which is a flavor of Unix, then our system can operate on that hardware. Could be a Raspberry Pi. As long as it's got 4 gigs of memory and up, we can use it.
Very cool. Any last questions folks would like to throw into the chat? Please do so now. Fantastic. I think you covered us nice and well, Delano.
Right. Yeah,
Thank
give
you.
us a try.
Yeah, I appreciate you sharing your time and expertise today and giving us a good overview of the EDJX platform. Laura has shared her email address in the chat. And as I mentioned, we will also be posting the session to YouTube shortly if folks would like to refer to it on Riot's YouTube channel. Delano, Laura, thank you so much for being with us today. We appreciate it.
Thank you.
Thanks, Rachel. Thanks, Lauren. Thanks, Riot. Appreciate it.